In the last video, we looked at some parallelograms in GeoGebra and kind of formed some conjectures about properties of all parallelograms. We thought that a parallelogram would have opposite sides that are always congruent to each other. We thought the opposite angles would always be congruent to each other. And we thought that the consecutive angles were always going to be supplementary to each other. They wouldn't be congruent because one would be acute and the other is obtuse. But if we put them together, we'd form a straight angle. And we wrapped up that video by saying that in order to figure out if our conjecture is true or not, we would either need to come up with a proof or a counterexample. In this case, all of these statements are absolutely true. So we're going to start working on proofs of this. And I want to start off by saying that I'm going to show you how I would go through these proofs if I didn't really have any idea of how to go forward, as long as I had some key things that we've been building over the past few weeks. We've kind of got our toolbox here. All right, so one thing I've got is the filled out handout that I have about all the reasons for proofs and when we could wind up using them. I've got my handout of all of the different triangle congruence criteria. And I have the start of the quadrilateral reference sheet that we're working on right now. So I want to give you a sense about how these things aren't just here to make homework for you and make grading for me. These are things that can help you to build proofs. All right, so let's take a look at our document camera. So we're given ABCD and we're given that it's a parallelogram. And in this case, we just want to prove that the opposite sides of this parallelogram are congruent to each other. And I'm going to prove this using the flowchart method instead of the T-chart. It's exactly the same statements and exactly the same reasons. It's just a different structure for drawing it that makes a little bit more clear how statements lead to other statements. So how do we start writing proofs? When you just have a blank sheet, how do you get started? Well, a lot of people know this right off the top of your head, but you're going to start with the given statements. You use that at the start of a proof. And the statements are either given in words or you can see them on the diagram. So in this case, there's nothing marked up in the diagram here. All we have is that we're given that ABCD is a parallelogram. So that's going to be the top statement in our waterfall. ABCD is a parallelogram. Parallelogram. Never give myself enough room. I should write the statement and then write the box. Okay. So where do we go from here? We've used up all of our givens, so we're kind of stuck on that. Let me get out my reason sheet again. So we've got a vocabulary term in our given. Notice how I highlighted this so that I'm not just looking down this side. I've got some highlighting here to help me think about when to use it. So, but parallelogram is a vocabulary term. So if I break that down into what parallelogram means, then I might have some statements. So what does parallelogram mean? Well, I'll go to my quadrilateral reference sheet. And a parallelogram is a quadrilateral with two pairs of parallel sides. Okay, so I know that the opposite sides of this are parallel, so that I know that AB is parallel to CD, and I know that AD is parallel to BC. Okay, and what's the reason that I'm going to use for that? I was using this step right here. So that's going to be the definition of which term is it that I'm using here. I just used the definition of parallelogram. And I'll just draw a parallelogram. Your statements have to be clear. The flow of your logic has to be clear. But you can use abbreviations and symbols when you want to. The person reading your proof is on your team. They want to understand your argument, but you have to make an argument that's complete, and you have to make it at least clear enough that they can follow. And I've got arrows leading to these two boxes because I needed this statement to be true. I'm not just using the definition of a parallelogram. I'm also using the fact that this particular quadrilateral is a parallelogram. All right. Once again, I've got, I've gotten a little further, but once again, I'm going to go back to my reasons and proofs and see if I can figure out how to go forward from here. This looks really confusing to me too, because so far we're really used to dealing with triangles and proofs, and we don't have a triangle here yet. So this is a little bit unsettling. But let's see, we've got some parallel lines here, and I remember parallel lines are kind of important. That was one of the things that I highlighted. Oh yeah, when I see parallel lines, I should think about the alternate interior angle theorem. So alternate interior angles can help me if I can spot the mark of Zorro. All right, so I'm going to take in yellow, I'm going to mark that pair of parallel sides in yellow, and I'm going to mark this side of parallel sides in pink. And even though in this proof we don't have a mark of Zorro here, there's nothing that stops us from drawing in a line that's going to make a mark of Zorro. So what can we do that's going to let us do that? Well, we could really draw either of the diagonals for this. That's going to give us, for instance, if I draw this diagonal right here, I'm going to make it a dashed line. This is what we call an auxiliary line. Remember, like the aux cable in going into your television. This is true for all. This is going to be true for all parallelograms, whether or not there's a diagonal shown or not. So where can we see the mark of Zorro now that we've got that dashed line coming in? Well, that completes a yellow triangle here. So that's kind of cool. So what two angles are congruent to each other because of that yellow mark of Zorro? Well, there's our yellow Z right there. So this angle is part of that. And this angle is also part of that. So we've got to name these angles using our three-letter code. So this is angle, all kinds of different names for it. Angle ACD could be a name for that top angle. And the bottom angle we can call CAB. All right. And what's our reason for that going to be? What reason did we read off of our proof list? Parallel lines, mark of Zorro, this is the alternate interior angle theorem. Alternate interior angles. And once again, I need to have an arrow leading into this because I'm really using two facts. I'm using the alternate interior angle theorem, but I'm also using this key fact. I needed this top and bottom line to be parallel in order for the alternate interior angles to be congruent. So that's what that arrow is indicating here. All right, so that took care of the yellow side. How about the pink side? Is there a mark of Zorro I can draw here as well? I always find it's useful, if you can't quite see it, to kind of twist your diagram so that the sides are at least the top and bottom of a Z. And once again, we're going to look at this diagonal. And it's a backward Z, but that's okay. Zorro was, well, I don't know if he was dyslexic, but he was ambilexic. I don't know, I just made up that word. But this different Z has got different angles. So now that we know that those angles are also congruent. So one of those angles is angle CAD, and the other one I can call angle BCA. Once again, those are alternate interior angles. And once again, this is a consequence of the fact that the left and right sides are parallel. So I'm drawing an arrow from the place where we've got the fact to the place where we're using the fact. All right, that's kind of cool. So now we've got, not just do we have two triangles that we could prove are congruent, but we also already have two facts. All right, so now where is that third fact going to come from? We've used all of our givens, so unless we can squeeze extra information out of that, we're done with our givens. But there are a couple facts here that we can use, and we don't need any hypotheses to prove them at all. For instance, what about the reflexive property? Anything is congruent to itself, and we can use this whenever two sides share a side or an angle. So do this top triangle and this bottom triangle share a side? Yeah, they share this side right here in the middle. So that's AC. So AC we can say is congruent to AC by the reflexive property. And we don't need any arrows pointing into this fact because this is just true on its own. I don't need any supplementary facts to say that something is congruent to itself. So now that I've got these three facts, how can I work from here to prove that that top and bottom triangle are congruent? Well, you need three facts in order to prove congruent triangles. And so what I'm going to do is I'm going to get my triangle congruence sheet out. And this is something that a student last week said, oh, this is really helpful. Could you do that more often? And so I'm going to do that more often. What I'm going to do is I'm going to take another sheet of paper and I'm going to cover up one of the triangles. So I'm just looking at the three parts of one of the triangles. So there's one piece of information, there's another. These are the three clues we know just about this triangle. So which one of these 5 diagrams looks like one of that triangle? Well, we've got two angles here and we've got the included side. So two angles and the included side is the ASA theorem. And that clue is you didn't even really need the picture. The clue is right there in the name. Two angles and the side between them. All right. So that's enough information for us to say that triangle DCA is congruent to triangle. I should be really careful when I do this to make sure that my names line up. So I've got a piece of parchment paper here. All right, so let me just kind of D, A, and C. So if I flip this around to the other triangle, it's going to look like this. So if you've had trouble seeing corresponding parts before, grab a little sheet of parchment paper or maybe some wax paper out of your kitchen. If you've got wax paper, you might not be able to use a pencil. All right, so DCA, we need to track that same thing on this picture. So DCA goes from here to here to here. So that's BAC. Did you see what I did? So DCA, once again, D to C to A, when I lay that on top of the triangle that it's congruent to, it shows me the path of vertices that I need to name the corresponding congruent triangle. D to C to A, it's that path right there, which is BAC, triangle BAC. And the reason we came up with for that is we said we've got two angles and we have the side that's between them. And just like we needed 3 pieces of proof for this, these are the 3 pieces of proof that we needed in order to establish this fact. So when we're doing the flowchart proof or the waterfall proof, we just want to make that clear. And on one side, it's a little extra work, and on the other side, it really helps you to kind of see how all of the pieces are being used in the proof. All right, And so we've proved that these two triangles are congruent, which is neat, but it's not what we needed to do. We needed to prove that the opposite sides of the triangles are congruent. And once again, let me go to my tracing paper. All right, so we want CD, so that's this side right here. And notice how when I flip this around to the congruent triangle, that its corresponding part, the corresponding part of the top side, was the bottom side. Okay, so DC lines up with AB when we do that. So those two sides are corresponding parts of these two congruent triangles, and that makes them congruent. So we know that AB is congruent to CD because, putting that into an acronym, those are corresponding parts of these two congruent triangles, and so they must be congruent. Those sides must be congruent because they're parts of congruent triangles. And how about the other two sides? Well, AD would be that side right there. What's the corresponding part on the other triangle? On the bottom triangle, again, if we rotate that around, that lines up with BC. So AD and BC are also corresponding parts of those two congruent triangles. So AD is congruent to BC once again because of CPCTC. CPCTC, remember, it helps us to say that once we've proven that two triangles are congruent, we know that all of their corresponding parts have to be congruent to each other. Not just the three we proved, but also the three parts we didn't use. Notice how we could also use this to say that angle D is congruent to angle B, because once again, those are corresponding parts. And that was one of the things that we wanted to prove, but honestly, I want to do that in a separate video. We'll take care of the angles in a different way, just talking about parallel lines instead of talking about triangles. So that was, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. That was a pretty long proof, but you can see how going through with my reference sheets, I hope you were able to kind of follow how these things exist. If you did them, they're friends that can help you solve proofs. If you didn't do them, then you're not going to get credit for doing them now, but you can still do them, and they're going to be there to help you when you're having trouble doing proofs.